I've drawn this a little bit more precisely in the following picture. Here again is a curved mirror. Here again is a light coming from a flower, and in red I've drawn all the light rays coming from the top of the flower. And they all hit the mirror at different places, and I'm using the law of reflection. This angle is equal to that angle, or this angle off the mirror is equal to that angle off the mirror. And our mind doesn't process all that, and so it tends to take all these light rays and extrapolate them back. So this light ray, if it's coming out like so, we tend to extrapolate it back behind the mirror. This light ray, if it's coming out like so, we tend to extrapolate it back behind the mirror, and we think that they originate from right there. And by the same token, if I take light rays off of the bottom of the flower and they emanate off in different directions, I tend to extrapolate them back until they reach right there. And now I see an object, which isn't really the object. I see the image of a flower, and it's behind the mirror again, just like it was with a flat mirror. But notice something important here. This image is considerably smaller than the actual object. Notice how much bigger the object is. So curved mirrors have the potential to change what we call the magnification of the object. The magnification is defined as the size of the image divided by the size of the object. So something with a magnification larger than 1 looks larger than real life. Something with a magnification less than 1 looks smaller than real life. This would be an example of a magnification less than 1. It's also true that this image looks upright. In other words, if the flower is standing here in front of me, then it still looks like it's in the same orientation as it was. As we'll soon see, not all images look that way. Here's an example of another kind of mirror. It's a curved mirror as well, but it is more specifically called a concave mirror. As I mentioned before, concave means it's pushed inward like a bowl, and if this is the shiny surface here, then rather than being bulged out, it's pushed in. We should again think about drawing perpendiculars to this mirror at all different places where light can hit it, and then using the law of incidence equals the law of, or this angle of incidence equals the angle of reflection to tell us where light should go after hitting the mirror. So if this is the center of curvature right there, this is a circle, and it has an origin right there at the center of the circle, then these dotted lines represent perpendiculars to the mirror at different locations. This light ray that happens to go right through the center of the curvature and comes down should travel straight back because it's traveling along the perpendicular. This light ray, which is coming into the perpendicular at a certain angle, should leave at the same certain angle and should go back like so. This light ray is coming into the perpendicular at a certain angle, and it's a little bit bigger than the last one. And it looks like it should come off like an angle like that. Notice that all these light rays, if I drew them correctly, more or less intersect right there. And if the top of the flower is actually right here, we would actually see where's the point where these light rays converge or appear to come from. We think that would be right there. If we were to do the same for the bottom of the flower, we would see a picture like this. In other words, the magnification is less than 1. It's a smaller image, and it's what we call an inverted image. It's an image that looks upside down, and we will see examples where when we look in the mirror, we actually see something that looks upside down compared to real life. In this case, although the flower is standing straight up, when we look at, and we are the observer down here, looking back toward the mirror, we see light rays appear to come from down here or from up there, and the flower looks upside down compared to real life. So we will see examples where different kinds of mirrors, in this case the concave mirror, produces an image that's both inverted and demagnified or smaller than real life. That's not always the case with concave mirrors. If we put our object very close to the mirror, like in this picture, and the center of curvature is way back here, and we were to draw, again, examples of light rays coming into the mirror at different angles, like so, and again draw perpendiculars along those parts of the mirror and extrapolate them back to the point where they would meet, our picture would look like this one. They never actually do meet out here in front of the mirror. They only appear to meet back behind the mirror. And notice that this image is actually bigger than the real object. This is a magnification greater than 1, and this is what we refer to as an upright image. In other words, it's in the same orientation. If the object is pointing up, then the image is pointing up. And the only difference is we would take the object that was originally out here and move it close to the mirror. And as a result, its image changed from being inverted and demagnified to upright and magnified. And all it took was just moving the object closer to or further away from the mirror. So we'll see examples where, as we start working through some of the algebra, we get different sizes and orientations of images just by virtue of the placement of the object in front of the mirror. And notice where the image takes place. Here it's behind the mirror, as opposed to the last example, it's in front of the mirror, also changes. So we'll have to learn a little bit about manipulating where is our perceived location of the image, how far back into the mirror or in front of the mirror is the object.